So good afternoon, good morning, good evening, everybody. Thanks for attending this new IEEE Sequence and System Society Rio Grande do Sul.
Good afternoon, good morning,
talks.
good evening, everybody. Thanks for attending this new IEEE Sequence and System Society.
Okay. So
good afternoon, good morning, good evening, everybody. Thanks for attending this new IEEE Sequence and System Society.
Okay.
So good afternoon, evening,
So sorry for this mistake of audio. So good morning, good afternoon, or good evening. Thank you very much to join us today for this new CASS talk. So today we have a talk that is organized by IEEE Sequence Systems Society Chapter Rio Grande do Sul, together with IEEE Sequence Systems Society Chapter Guadalajara. So today we have the pleasure to have here Rodrigo Calderón Rico from Apple. So thank you very much for accepting our invitation. So before starting your talk, just some announcement of next events. So next week we are going to have always the same hour, always Friday. So by Professor Yongqing Sheng from Beihang University, China, talking about reliable and low power design for STT-MRAM. The week after, we have a talk by Professor Sachin Sapatnekar from University of Minnesota, USA, talking about automating analog layout, why this time is different. And the last talk of March will be with Professor Luciano Host from Loughborough University, England. He's going to talk about early software error assessment of embedded deep inference networks. Also, if you want to see the talks that were organized last year, you just have to address this YouTube channel of IEEE CASS Rio Grande do Sul, where you have all the talks done last year. The recorded versions are available. Also, you have there the series of industrial talks showing a panorama of the microelectronic industry in Latin America. So we have 20 talks listed there. There is also the talks related to the last CASS workshop 2020, with also very well-known and nice speakers, and also the talks related to the digital processing of visual signals and applications workshop from last year, as well 5 talks from the South Microelectronics School in April 2020. So talks from France, from Taiwan, Chile, Colombia, and the USA. So the next edition of the South Microelectronics School and the South Symposium Microelectronics is end of April. So the call for paper is open till end of March. So it's open to anybody from anywhere that wants to participate. And soon you are going to see the program of the school. Also, end of July, it's planned to have a seasonal school on monolithic 3D, where the following editions should be in France, Singapore, and China. The order is not yet confirmed, but these are the schedules. Also, the 4th edition of the seasonal school of physical design automation should be done in August. Past editions were in Porto Alegre, Chiai, Taiwan, Beijing, China. Ceresa 2021, the 17th edition of the International School on Effects of Radiation on Embedded System for Space Applications. We hope to be able to do a face-to-face event in November. So soon also you should have the program. And using this opportunity that if you want to promote and to do any activity under the scope of IEEE Circuits and Systems Society, it's very simple. First, you must be a member of CASS Society and acting in a CASS chapter or CASS student branch. So any member of the society, not only the members of the board, can propose activities. So then you can prepare your proposal to the CASS chapter or CASS student branch. And then CASS has several calls with funds to support several activities. So one is the student design competition. All these you can go to the CASS webpage to see more details. There is the CASS outreach calls, a call for seasonal school, a call for pre-doctoral grants that allows students to spend 2-3 weeks in another lab abroad. The student chapter grants, so there is a new call that should be announced soon. The student travel awards, so that can help you to participate in CASS conference. Now the virtual editions of some conference, you can ask for the support for your registration. So several paper awards, also the Chapter of the Year awards that also give a monetary grant for the chapter to do more activities. And there is many other society awards that you can see in the web page. And there is also the CASS Distinguished Lecture Program. So this is just a brief overview of some of the possibilities you have to organize activities with the financial support of CASS. Then also be aware that it's still available, the discount from IEEE for student and graduate student membership, where you pay 50% of the annual fee, and you just have to use this code Future50, and that's it. So I hope that if you are not yet a member, that you consider to join now. So today we are here to attend Rodrigo Calderón Rico from Apple to give a talk about missing hardware functions to apply intelligence in communication system. So Rodrigo Calderón Rico was born in Guadalajara, Mexico. So he received the bachelor degree with honors in electronic and communication engineering from University de Guadalajara in Mexico. And then he has done the master studies at Universität Bremen in Germany, receiving the master in communication information technology. Then he concluded his PhD degree at University of de Guadalajara in computer and electronic science, focusing on cognitive radio communications. Before joining Apple as an architect for display and sensing technologies group in Cupertino, California, he worked at Philips in the area of healthcare in the USA, improving receiver capabilities for MRI systems, and at Intel Labs Mexico, developing new wireless communication technology. He was a part-time lecturer at the Technology Center in Guadalajara, teaching communications and signal processing. His research interests are communication, signal processing, hardware architecture, and neuromorphic processing. He has made contributions to intellectual property and holds several patents. He has been the receiver for numerous journals and conferences, and he is the chair of the Signal Processing and Circuits and Systems Society in the IEEE Guadalajara section. So thank you very much, Rodrigo, for accepting our invitation to give a talk today. And now the floor is with you to start your talk.
Thank you very much for the invitation, first of all, Ricardo and everybody. So today's talk is about cognitive radio and missing hardware functions to apply intelligence. Sometimes you hear the buzz of new technologies and new theories and theoretical backgrounds like artificial intelligence and among others. However, when we look at what technology is available and what is possible to be implemented in real hardware today, there is a big gap into what things can be done and what things cannot be done. And today's talk is about getting into that perspective with some examples using cognitive radio and some communication schemes. And at the end, with one application for the MRI systems receiver, where we could understand more what I mean by intelligence portions that are missing from the hardware. And sometimes it's not just about algorithms and we can implement them as artificial intelligence and we are done. But more to that is how we can make the connections between the hardware and the software and make a system, a cohesive system all together. So let's get into the talk then. So we started with a basic chart of what the communications drivers are. So we look at the throughput, size, latency, power, flexibility, all of them together, getting to achieve the best of each of them. And sometimes you have to, or most of the times you have to make a compromise and a trade-off, which one you have to give off, and then which one is your priority for your specific application. So the architect of building the communication systems need to balance all these traits, among others, that will make the application feasible, implementable, and also efficient. So then we look at the use cases. What functions do we need to implement, and what do we need to get there? So when we get into that, we also have to look into the user interfaces, the environment where it's going to be playing in or is going to function, acoustics to the system, temperature that has to resist, regulations, and I include here also mechanics, but also is very, very important to look at what deformations the system will have in the field. So getting into the example of the cognitive radio, first of all, as a engineering sanity check, we have to define what is a cognitive radio. So in a nutshell, cognitive radio has to take many different parts of different branches of the theory, like transmitting power control, like control theory, software definition concepts, how to implement these functionalities into software. We have to understand what is the spectrum management, because we might end up using a spectrum out of the range that is allowed by certain frequencies. For example, if a carrier needs to transmit only on a certain spectrum, the cognitive radio tries to get more out of that. So even if you are assigned a specific spectrum chunk, you could use another portion of the spectrum that doesn't belong to you, and then you will become a secondary user of that spectrum. So that is very important to extend the capability, the capacity of the channel. So then now we will look at different problems that we have to solve, like adaptability. Then we have to have awareness where we are operating, because not all the carriers in different countries uses the same spectrum. So you have to apply policies as well. So with that in mind, we have to also include competition and cooperation among the same transmitters and receivers. So we have to include maybe some hardware flexibility to adapt to the configurations of the system itself. We have to include maybe some theory for stochastic games as well. And then we gluing all this together, we might end up having a cognitive radio with a maybe including some of the algorithms for artificial intelligence. In a simple terms, cognitive radio describes the evolution of the radios to highly adaptive communication systems. So a cognitive radio is a software-defined radio that adds additional senses to the environment and tracks changes and possibly reacts to them upon findings. Okay. So by learning about the environment, we can use this knowledge and apply it to improve the communication system. So let's get into the example itself. So we take it into the example of a very classic problem in communications. So it's the equalization of the channel. So when we have a transmitter, and we have a transmitter and we have a receiver, we know that we have to have we will have a channel to pass through, and we will be impaired or affected by noise. And not just the noise into a single band. This noise can be different in different bands, I mean the spectrum, so that they don't see the same amount of interference. Okay, so that's the concept of the equalization. Then you have to consider these effects at different channels, so that you have, when you look at the spectrum, ideally in the receiver you will see a flat spectrum with equal power, but due to the channel impurities you will have a channel that is fluctuating, and this fluctuation depends on the channel type, but also this channel type can change over time, and instead of having slow changes, it can have very rapid changes as well. So we need adaptability there as well. So there is a very common technique in communication systems, which is OFDM, where we have a chunk of the spectrum where we can use, and then we divide this into subcarriers. And for each subcarrier, we assign a certain amount of information. So when we do that, if we were to send all the information at once without giving any information to the receiver about the channel statistics, we will not be able to apply any equalization. So that's why we need to include among the carriers with data some pilots insertion in between, so that we can sample the channel. So the transmitter will know the power of this pilot, and the receiver will know also the power of this pilot and the code of this pilot, so that when it receives the pilot at the decoder, it knows by difference what was the effect of the channel at that time. So if we include several equally spaced pilots in this spectrum chunk, we will have very good probability to make good equalization of the receiver. So in mathematically speaking, we have on the right side here the receiver signal, which is Y, and then we have the signal, which is U plus some noise, and the U is affected by the channel H. So when we look at this problem, actually what we want to know is how H was affected by channel. And we look at different techniques to estimate the channel. So for example, MMSE channel estimation, where we have the noise as a factor, so with sigma square. So we take the noise knowledge as a factor to recover the information from the channel. So to estimate the channel error, we know that we have a pilot set that we know, minus the estimated channel, which is H hat, and then we'll have to look at the correlation of it to get the actual estimation channel. So at the end of the day, we need to have a good estimation for the channel, and it is proven that if we do equally spaced pilots under a specific chunk of spectrum, it will lead to an optimum equalization method for the channel. So that is for the classic, let's say, state-of-the-art transmission with OFDM when they started like 20 years ago. But what happens when we have a cognitive radio in play, where what happens where we have to use a spectrum that is not assigned to you. And then we have an additional layer of operation in the communication system where we have to include the subcarrier assignment block, where we have to look at the spectrum that we are allowed to use each transmission time, and then assign the pilots and the data in the next block of transmission. And then the receiver has to know as well, has to work in synchronization with the transmitter so that the pilot positions are known at the receiver as well, so that we have, again, a known pilots set at the receiver. So, but now the paradigm changed here because we don't know if the pilot assignment is going to be equally spaced or is not going to be giving us a good sense of what the channel changed. So let's imagine the next example. So here is better explained in this slide. So when we have in the regular scheme of OFDM, we have assigned the data and the pilots equally spaced. However, when we include in previous block scheme the subcarrier assignment, some of those carriers will not be used or cannot be used because somebody else is using that. So how do we solve that problem? Because now we already said that the ideal scheme to estimate the channel for optimal equalization is to have the pilots equally spaced. So now when we have the problem that the pilots are not going to be equally spaced, you will end up having pilots and data that will no longer cover the rapid changes of the channel. So let's say if the channel doesn't change much, you only need, or doesn't change at all, you might only need one pilot, right, to estimate the whole set, the whole chunk of the spectrum. But since we don't know how fast the channel is changing, or if it is slow, even if it is slow, you will need more than one pilot to estimate accurately the spectrum for equalization. So when this scheme it gets into play, the equally spaced pilot is no longer true. And we can see it here on some of the simulations that I made here and plotting here. So when we have a perfect knowledge of the channel, I'm plotting here in blue in the curves how the estimation at the receiver will look like, ideally speaking. So if we have all the information, from the channel, we will equalize the channel with this set of pattern for equalization. Now, since we don't have the complete set of information of the spectrum, how the channel changed, we only send a few samples of it. Then we will see that the spectrum estimation is not exactly accurate, right? So we have to get better and better to follow the blue curve to get a good estimation of the channel. So the problem in a nutshell is, how do we estimate the channel so that we get a very accurate equalization of the receiver? Okay. So let's. So now, how do we solve this? And if we look at the problem itself, we need to understand about the changes in the spectrum and how the spectrum changes. And maybe we need some additional tools to understand further how actually the spectrum is changing. So there are different proposals to solve this. One of them was to assign, in the previous slides, for example, instead of looking at equidistant pilot tones, it is calculated in this proposal of Hu and He. it is a proposal so that we can move the pilot position under a certain, let's say, distance from the original position, and then you will have a good approximation to the channel, to the ideal channel. However, this is always fixed, right? So you will always have this position, and then from that position, a certain distance in the spectrum so that you can move around the pilot tone. If, let's say, this one and this one were not allowed to be used, and either this one, you could move maybe this pilot tone here so that you could get a better estimation. So now that you have the pilot tone here, you have another pilot tone here. Instead of having the distance very wide, now it is a shorter distance. So coming back to the other tools available that we have, the way we look at this problem is to how we can understand better the spectrum. And one of the tools that we use to understand that is the wavelet, the composition of the channel. So each transmission time, we take whatever pilot scheme we send into the OFDM chunk, and then at the receiver, we analyze the spectrum based on that information data. And what we realize is that we need to understand where the deep changes in the channel are happening. So really, the information we are looking for is not only like the channel is changing in this spectrum position by this amount, but how much is changing. And since we have limited positions to assign to the pilots, we need to be very careful where we assign those pilot tones. So if we analyze the spectrum at the receiver, we understand that we can assign the pilots where the deepest changes in the channel happen. And then we will be more focused on those changes than the ones that are not really affected by the channel. So for example, if we assign all the channels at the center of this graph where the channel really have a great dip, then we will have more knowledge than if we assigned pilots equidistantly in this spectrum domain. So all in all, if we divide this assignment of the pilots in 3 different sections on this example, we will achieve better precision than if we send it equidistantly. And this changes the paradigm of thinking about only equidistant pilot tones in the OFDM block. So we do the math, and based on the math, we understand that what we have to do is to look at the spectrum of the channel, doing the discrete wavelet transform, where the channel is greatly more affected by a constant beta. So basically what we are saying is we define a certain threshold in this, for example, in this simple example, we define a certain threshold with the channel changes, and then we look at that position, and then we assign the pilot in that position. But by doing the composition of the discrete wavelet transform and assigning a threshold to that, and by the way, this threshold can be dynamically adjusted. In this case, we leave it fixed for the specific channel. But if you have different channel or the channel is changing rapidly, you could implement an additional algorithm on top of this so that you can dynamically change the threshold where you will be looking at the changes of the channel. Okay. So let's go to that. So by doing that, we look at the performance results in the bit error rate, and it was we had very good results because what we look is that for example, in the figure on the left, we have the blue curve. So this is if we know all the information of the channel, meaning we only send pilots in the OFDM block, we will achieve this performance on the blue curve. So now, with the proposed scheme that we had in the red curve, assigning 32 pilots in an OFDM block of 256, we know and we achieve about 1 dB away, 1 dB away from the ideal channel, which is really, really great, right? Because we are only 1 dB away from the ideal case. If we use only 4 blocks, 4 pilots in the block of 256, we see that we have very flat and very poor performance, okay? But it is expected, right? Because you are only using 4 pilots in a chunk of 256, and as you increase the number of pilots, you see that the performance is getting better and better. And then 16 with cyan curve, and then we get into the red one, which is only 1 dB away from the ideal case. So looking at the spectrum itself, so if we look at the spectrum by using this scheme, we follow almost perfectly how the channel changed, right? If we go back and compare to the first scheme that we have here, that the ideal, it is the blue one, and then the estimated one is the pink with the blue, well, sorry, with the pink with the green pilot tones assigned. Then we have this performance here. But with this scheme, understanding the spectrum, we're getting to an almost perfect knowledge of the channel, right? Which is really, really improving the performance of the system overall. So now, what do we learn from this example of the channel equalization on the cognitive radio system? So I will read briefly the points here. So contrary to the former cases in this work, a new pilot allocation algorithm for the OFDM based on the cognitive system has been proposed, and an optimal solution it is found, and it went away from the classical proposal of having equidistant pilot tones in the spectrum, but assigning a non-equidistant pilot scheme into the system. So I think that's the main takeaway. But more importantly is when we have faced a problem, we look into mathematical tools that could help us understand the problem, and then do a proposal. How do we implement it into the real system? So discrete wavelet transforms, for example, are known for so long time, but the main let's say benefit of using these tools is when we look at the right application for the right problem. Now, this scheme is more very explained in this case, so that what is the part that is making this system intelligent or adjustable to the conditions of the channel. And we look at the block of this channel estimation strategy, but also if we look at this loop here, we need to have a coordination between the receiver and the transmitter, sensing the spectrum, how rapidly it's changing. So it's an additional parallel block to the communication system, so that is telling us with a few microseconds or milliseconds, depending on the frequency you are operating, an estimation of how the channel is being used. Not exactly how we have to sample the spectrum, but the chunks that are not assigned to you in the transmitter, and you can in the spectrum that you can use. So basically, what I'm saying is that in a regular communication system, you have a spectrum assigned, and in this scheme, you have either one chunk of the spectrum, or you will have several chunks of the spectrum parts to transmit. And that's what this spectrum sensing is telling to the system. And then the contribution of that work was in the channel estimation strategy to improve the system with what already knew. Okay. So now we look at another way to resolve this problem, and we look at another tool that again is being used for so long in the theory, at least, and it is the spectrum assignment in the modulation scheme with a chaotic sequence. So in this case, we have regular QPSK symbol scheme, and then we might say we scramble the symbols, right? We scramble the symbols with a known sequence, and this sequence turns out to be defined by a chaotic sequence. And a chaotic sequence is nothing but a sequence that can repeat itself all over again with a certain pattern. So when this pattern is known at the receiver, you know how the scramble happened in the symbols. So this is, again, opposed to the regular thinking of what a modulation scheme is, because instead of transmitting the symbols in this way, you will not have no longer 4 symbols, but you will have a number of symbols depending on the sequence or the chaotic sequence that you are applying to it. So if you have an equal number of symbols, let's say 256, instead of modulating with the QPSK with a specific symbol in this way, you will assign it with this specific chaotic sequence in this way. So instead of transmitting this, you will be transmitting this, which again, it goes against what normally is being used. And what are the results here? Because even if you transmit this sequence, the receiver needs to know that as well. But now, the way the receiver needs to work in this solution is we look at the correlation of the chaotic sequence, and on top of what the probable symbol will look like. So we look at each symbol at the receiver, and then we apply the correlation of that symbol against a possible symbol with the chaotic sequence. So basically what we are doing is applying the correlation of the chaotic sequence to the modulation scheme, nothing else than that. And then by using that superposition, we get a very good results on the assignment of the. So basically, we don't longer need pilots here. So the pilots are the data itself, right? So what we are doing basically is that we don't need a channel estimation strategy. We simplified the communication scheme by eliminating these blocks and only including chaotic sequence modulation in the symbol assignment with the QPSK, for example. And that simplifies the system. And then we have also good results. And this is, again, saving in power, and then saving in latency as well. So a final example with this very classic circuitry here. So what we are looking at is an MRI coil that is used in the MRI scans. So what it does is basically act as an antenna to receive the impulses from the body, and then based on some blocked equations, we have to recover that signal and translate it into the frequency domain with the Fourier two-dimensional Fourier transform to obtain the images that we see in the MRI scans. So the way it works is that you have in the MRI scan, you send some signals into the body. The atoms of the signals, the atoms in the body react to the signal, and that's what the coil should sense. Okay, so that's in a nutshell how the MRI works, and based on the tuned Lamar frequency. And then now we look at the circuitry here. We have active detuning circuit, which is in this portion here, marked as number 1. We have the MRI coil, which is a regular coil with specifics of the frequency of the Lamar frequency. An isolating matching network because it has to switch really fast, and low noise amplifier is very important, and then a balance circuit to do some filtering there, and then all the information sent to the receiver to reconstruct the image and generate an image of the body. So when we look at this specific circuitry, in a classical thinking, you might say that this circuit is complete, right? And the system is complete because you fix to a certain frequency, to internal Lamar frequency, and then you start doing the operation regularly. But the way the system works is that it has separated the functions of the active detuning and the tuning and matching away from the receiver itself. So these functions here are managed by the system itself, not by the receiver. So what happens there is that when you don't have a complete control of the information you are receiving, and then somebody else is tuning these other two functions, then you will have disconnection between those two. Or if it is not a disconnection, it's going to be a non-optimum system. And what I mean by non-optimum system is that instead of these functions being managed by the system, if they were managed by the receiver itself, it could do much more here, because when you have the tuning and matching, you could do equalization right into the receiver function, and then tune those matching and tuning, so that when, as we saw in the previous example, when we see the channel changing, because remember the coils that are, if you haven't had an MRI in your life, the way it works is you lay on the table, they put on your body, on top of your body, on the skin, some of these MRI coils as sensors, and these sensors are not they are connected to the system, but they are fixed, right? So when you see these and you are moving, so the patient is breathing, right? You cannot stop the patient breathing. And what is preventing a good image in the MRI system is this movement precisely. So you have to be almost standing still in the MRI system so that you can catch a very good image. So if based on this movement, you can have a rapid respiration or a slow respiration, or you can almost have stand still depending on where the MRI coil is sitting. But again, this movement implies that the channel is changing. But if you don't have this equalization right at the receiver, you will not be improving much at the system level what the signals are looking like, because they are already affected by the channel, and you are not correcting at the receiver anything for those changes from the patient, right? And the same happens with the frequency here. So if you are looking at the Lamar frequency and you have a tuning circuit, you could basically use the same MRI coil to scan different frequencies and make a different type of studies, not just for the MRI signals. Okay. So I hope this example here highlights better what missing pieces of the hardware need to be integrated into the receiver so that you can build more intelligent systems rather than just looking at the higher level at the system and trying to apply machine learning and things like that. For example, there is a huge trend into the MRI systems to apply artificial intelligence to reconstruct better the images that are captured. But that is already using the information only used after the receiver without looking into this specific tuning on the and matching of the network. So whatever you do on the top of the signal is going to be already affected by the impairments of the channel. If you are not correcting right at the receiver, yeah, even if you apply the most sophisticated algorithms in artificial intelligence or any other you can think of, you will not get rid of these specific impairments of the signal, which it might be easier and less and more cost effective than spending I don't know, maybe hours or minutes to reconstruct the image with other algorithms. This would be in real time. So then, what are the takeaways of these all of these examples is that to chip through intelligent radios in these cases, we need to consider all the potential cases and uses that include adequate signal information control of the flow of the data processing, meaning you have to look from the data acquisition, the sensors, what things you are capturing in the information, and then based on that, look at the end, what other algorithms you can implement to top of that. Always look for ways to minimize the number of components or the processing blocks of the data. Efficient architectures are inherently simple, but hard to conceive. That's true. While creating an architecture, the need to cross domains of expertise to implement them is very, very important. So if you want to be a good or you want to propose good solutions, you have to look into more ways or more mathematical tools that can help you to apply into the very specific domain and then extrapolate that knowledge and include it into your problem. Always keep the hardware dependent functions to the minimum and implement most of the processing in software. And remember, the software dwells freely inside the walls of the hardware. That's a true statement. So whatever you do in the software, it will be bounded by the hardware boundaries and the functions that you have there. So I have a final slide with some references, and might be small, but they will be available at your will. With that in mind, that would be all. Thank you. Probably I cannot hear you, Ricardo. Let me see.
Sorry, Claude.
Okay, good.
So if somebody has questions to Rodrigo, please do it as soon as possible in the chat channel. So thank you again, Rodrigo, for this interesting talk. So I have one question is about what are the main challenges that you are facing at Apple to improve the range of the communication systems, if you can tell something about.
Yeah, well, make the disclaimer, right? So there is nothing that I'm applying right now at Apple for the communication systems itself. So I'm working in a different domain, to the surprise of my career. So there is so the focus on my job right now is on the developing display architectures for improving the visual experience of the end user. And there are many challenges there. There are many challenges there. I can think of one is the miniaturization of the electronic components. So, for example, if we look at the LEDs, for example, that we have, there are systems that are called zero backlight or 0D or 2D backlight that you have in the 2D backlight systems, which are more complex. We have the two layers of the display. We have the first layer, which is the backlight of the LEDs, which are used for high contrast. And then on top of that, on that layer, you have an additional layer, which is the pixels themselves. And those two layers need to be in synchronization all the time, so that if they are not in synchronization, you will see the images very blur, or you will have flashing in your monitors. And one of the challenging things in those systems is how you keep those two systems synchronized, and how you keep also the power down in the first layer. So there are many articles actually in the IEEE or any other journals that look at the 2D backlight with the LEDs and ways to reduce the energy that the mass is a massive. Basically, what is the 2D backlight is a massive array of LEDs that consume a lot of most of the power of the complete system. And there are challenges there to how to minimize the amount of energy to light up the LEDs and still keep the performance of the display in sync. So two things there: synchronization, to keep all the massive network in synchronization, and power.
Okay, thank you. So another question: when can we expect to have the whole electronic circuits of iPhone in just one chip?
Can answer that. I don't know. I mean, honestly speaking, there are multiple functionalities that are getting into a single chip. So following the Moore's law, right? So if we look back in some years ago, not so long ago, I mean, you didn't have so many circuitries embedded into a single chip, and there is always the trend to try to put more and more into a single chip. So now, what are the challenges there is again, power. And you cannot include some of the high power components inside an SoC, right? So there are other ways that you could mimic part of the functionality of the analog power domain inside the SoC, but then the high power components, those are going to be still out of the chip, and those are going to be there for quite some time from now on. There is no clear path how to minimize those high power components and include them into a single package of the SoC. So I think that's a main challenge for all the researchers out there that are looking for materials and are looking for efficient systems and for high power. And by high power, I mean more than 5 volts, right? But to include those into a single package of the SoC. So those are tough challenges. I don't see to answer this clearly the question. I don't know when these systems are going to be popping up. it's a long road.
Yeah. Okay, so thank you very much, Rodrigo. I'm not seeing any more questions here from the participants today.
Okay.
So if you are attending this talk later on, so you can also send questions by email to Rodrigo. So thank you very much, Rodrigo, for this opportunity to know a little bit more about missing hardware functions. So it was a nice talk. Thank you again. I just would like to remind all you that next week, same hour, we have a new talk by Yu King Sheng from Beihang University. Talking about reliable and low power design of a STT and run. The week after, March 19, it's time of Professor Sachin Sapatnekar from University of Minnesota to talk about automating analog layout, why this time is different. And to finish the lectures in the talks of this month, March 26, Professor Luciano Ost from Loughborough University, England, will talk about early software assessment of embedded deep inference networks. So I hope to see all you next week. And if you missed the talks last year, all of them are available in the YouTube channel of the IEEE CASS Rio Grande do Sul chapter. Also consider to subscribe to the CASS Rio Grande do Sul chapter channel, then you can receive some news in advance. So thank you very much to all you. Thank you again to Rodrigo for this nice talk.
Thank you.
And have a good weekend and see you next week. Bye-bye.